Welcome to the EE degree concentrations workshop by IEEE at the CSULB branch. Today we're having guest speakers Ben, Dakota, Christina, Andrew, and Michael talk about the different concentrations that EE has to offer. But before we get into our guest speakers, IEEE is a club here at CSULB, but it's also a large technical and professional organization for the advancement of technology. And if you guys would like to get in touch with us, you can join our Discord where we post weekly updates on our events, projects, and different workshops. All you got to do is scan this QR code over here. And we'll begin with our communications major, Ben.
Hello, everyone. So my name's Ben Nepomuceno. I should be graduating in the fall of this year with the communications concentration. So as you can tell by the slide, I was a prior military. So I spent 9 years in the Marine Corps before I started going to school. And that's what really influenced my decision to choose communications. The monstrosity of a radio that you see on the left is an old Harris HF radio that we used to use on the equipment that I helped maintain. So that top portion is the tuner for the antenna. Then it was the transceiver. Then there was, because it could do VHF and AHF. So there was exciters for each of those for the different frequency bands. And then you had the amplifier, and then that bottom module was the power supply that was like 150 pounds. So every time that we had to change it out, I remember having to unscrew everything, pull it off the rack, and then, haul it to the warehouse or wherever that we had to replace it with. So when I was in, I didn't even choose communications or the job that I did myself. It was just given to me. I just, I was out of high school and I randomly was assigned to it. They actually, when I was in school, they went through, there was like 10 of us, and they started in the M's for whatever reason in the alphabet for the roster of the class. And they chose 10 of us, and then we ended up being radio technicians, and we also dealt with like computer systems that operators would use to control aircraft. So that was my experience, and that's what really piqued my interest, because there was an actual Northrop Grumman employee who was also a prior Marine, but he was kind of like a, how do I say this? He helped us troubleshoot problems that were too advanced for us. So if there was something that we couldn't fix, then his name was Mr. Berg. He would come out and then he would try and help us fix the problem. But he was actually the first one that told me, he basically gave me like a crash course of the same like circuits course that we do here at Long Beach. So he taught me about, RLC circuits. He's the first one that taught me about like different coordinate systems, because that's the radar that we used was cylindrical. So he told me about like going from cylindrical to XYZ. So I actually wasn't planning to get out of the Marine Corps, but then I met my wife, so I decided to make a career change. So I got out, I started going to school. At first I was undecisive, or I couldn't decide what exactly I wanted to do. But then after talking to some of my other friends who had also gotten out and gone to school and got jobs, I decided to choose electrical engineering. Currently, I'm actually working at Kaiser Permanente at the help desk there, because I got the job when I was going through a networking class back at my community college. And I just, the situation that has led me in has been helpful, because I also have 2 kids now, so time is short, and it's been easier just to stay there than to try to find a new job for me. But as far as the communications field, I mean, there's a whole plethora of different systems and platforms and things that you can do. Obviously, things like cell phones, the cell phone technology, anything wireless, Wi-Fi, 3G, 4G, 5G, not even 6G. There's different, obviously in the Marine Corps, I dealt with different radio systems. I am talking to some people that I knew out of Northrop. There was one particular radio system that we used. It's called Title J. So it was a military standard that was used to like transfer like the different aircraft tracks that would be received via radar, and a type of line of sight system. So it used different types of technologies like TDMA, time division, multiple access. It used frequency hopping. So that is something that I'm interested in. And then, well, also one thing I like to talk about, because I don't think it's mentioned enough. I know a lot of times, like if you take like EE 200 or other courses where they talk about different types of careers that you can pursue, everybody, or at least what it feels like to me, a lot of people like to do like the more technical side of things, research, where they're actually getting into like, you know, the nitty gritty. But there is the other side of it where I know, because I personally have a lot of friends that I was in the military with, and they transitioned, you know, they got their degrees, but now some people are like technical writers. So people have to make the documentation for all of the equipment that gets developed. You know, that doesn't, somebody has to do that job. There's also, as far as like education, so a lot of companies like Northrop or Raytheon, when they take the equipment to the user, so like, you know, the military to use, somebody has to teach them how to use it. And that's when I was in the transition from that monstrosity of a HF radio that you see to the green radio, it's called a PRC 150. Like that thing is maybe like the size of the oscilloscopes that you see in the labs at school. It's very small, and it does the same, actually it does more than what that radio does on the left. But when new equipment like that is brought out, engineers are the ones who have to go out and, you know, teach the users how to use it. So even though you may be wanting to like design digital filters or, you know, come up with some sort of different type of actual end products, bear in mind that there's also a plethora of other jobs out there for as far as sales, or, you know, in the Marine Corps, we talked about breaking things down Barney style. And there is a large need for people who have the technical expertise of knowing the systems that are being, you know, designed and implemented, and then also having to tell that to people who have no idea what a capacitor is, or, you know, even care. They want to know how the product works, so what it's going to do for them. And so don't shy away from jobs like that if they present themselves. So that's all I have.
Thank you, Ben. Do we have any questions?
Yeah, I have a question. So what would be your ideal job for you? You referenced a couple different routes you could take with it, but for you specifically, Ben, are you more in the idea of designing? Are you more in the idea of teaching it, or specifying it, or making those data sheets, etc.? What appeals to you more?
I would say more so with like being like whatever would allow me to talk to people. Because when I was in the military, I found out that's what I really enjoy doing. In the second half, because I served 2 enlistments. So my first enlistment, I was I was deployed twice, one to Iraq, one to Afghanistan. So I was actually like working on the equipment. I was troubleshooting. We worked like, you know, 12 on, 12 off shifts anytime I went overseas. So I was like, you know, I was in it. And then my second enlistment, I actually got sent to the schoolhouse. So I did something completely different. I was a teacher for my job. So I had to teach fresh Marines that just came out of boot camp how to fix all the equipment that we worked on. And I also did some technical writing, because we were in the transition of changing from the old equipment that you see on the left to the newer equipment that you see on the right. And so I had to write pamphlets of for all the new equipments, for like the new curriculum that we're developing. That wasn't as fun. So technical writing isn't, I mean, I could do it because I know I've done it in the past, so I would still be willing to do it. But I would say more so with maybe something with sales, or again, with being able to do the education or something along that lines, because I found that's something that I really do enjoy.
Awesome, thank you.
I have a question too. what was the transition like from the military to school? Like because you were like in comms, like did they actually teach you guys stuff about, you know, signals and stuff? So did it help smoothen the transition? Did I cut out?
No, Ben, I think you're muted.
Oh, okay.
Sorry about that. So yeah, actually, because for my particular field, it's like communications slash electronics. So it's like so in the military or in the Marine Corps, there's like they do it like 59. So it's always like 4 digits. So 50, it's like the first 2 digits signify like the field that you work in. So mine was communication electronics, and then the 2 other digits signify your specific job. So like mine was technically the technical air operations module technician. So in the 5900 field, anybody who gets a job like that, they first have to go through a basic electronics course, which is basically was abbreviated like circuits, like I think it's 211, because I didn't take I went to a community college, so I didn't take the 211. I think it's 211 that's at Long Beach, but that circuit course, I basically took an abbreviated version of it already when I first joined the Marine Corps. So yes, I learned soldering. I learned about, you know, RLC circuits. We used oscilloscopes, you know, Ohm's law. You know, I'm trying to think like different sorts of circuits theory, like Kirchhoff's laws and all that. Yeah, so I had seen that before, and then again, I was lucky to have the Northrop Grumman employee Jim Berg, who, you know, because he went with us both times that we deployed. So once my shift was over, I would just be sitting there, and so sometimes I would just go over to. He had his own little like 10-foot trailer because he was a civilian, and I would just go over there and, you know, talk to him, and he was so technically savvy that you know, there'd be a question that came up while I was working, and I had no idea how it worked, or, you know, because back then we're talking 2008, 2009. I was 21, 22. I was like, I went straight out of high school, so I had no, like, I barely, to be completely honest, I barely passed high school. I graduated with like a 2.5. I only did algebra 2. And so I wasn't very privy to what I like as I am now. So he had to start from like ground, like college algebra basically. And, but he liked to talk and I liked to listen. So yeah.
Okay. Yeah, because I was always interested. I didn't know they taught you guys all that, because I just remember we would just come to you guys just to like fix our radios and stuff. But and then last question, how much were you benching in that picture, man? Because your arms looking thick in that picture.
Back then I was probably benching like 365
Damn,
for like 2
bro.
or 3 reps.
All right.
Flex off is so real.
I had to ask, man. You put the picture there, man. The picture's right there. Look at that.
That's the only picture. Yeah. That was the only picture I had, that because that those Humvees, like, we would actually dry out and they were like filled with racks of radios. So that's the only picture I had that had like equipment in it as well from the Marine Corps. But yeah.
Gotcha. Thanks, man.
Do we have any more questions for Ben? All right, thank you, Ben. Next up, we got controls being presented by Dakota. So yeah.
So hi everyone, my name is Dakota, and I'm going to be graduating this fall with emphasis in control systems engineering. And hold on, let me try and grab annotate. Okay. And you know, when I transferred back here to Long Beach back in fall of 2019, I didn't even have any idea that we were supposed to choose a concentration. And so like towards the end of the first semester, Fei Wong told me I needed to choose, and I kind of started freaking out. I was like, I had no idea, you know, anything about any of the concentrations. So I did a quick Google search and I got these pretty, like Ben was saying, pretty technically savvy definitions, and that didn't help me at all. So I kind of found myself right back at square one. But then I decided, let's look at pictures of controls engineers. And I found this guy named James Jensen. And I clicked on this picture and it took me to a website where he kind of explained what is control systems engineering and what does he do and why you should do it. And he kind of helped paint the picture for me on what the job could look like after graduation. And so I decided to go with controls. He pointed out one thing, that if you like to tinker with things with your hands, if you're mechanically inclined, then control systems would be good for you, which is something that I like. Growing up, I always liked to work on cars and build things with my hands. So I kind of went to his website and saw what he was doing with this project. This is a drone that he's using to film landscapes with this giant camera, shooting 4K. And I had actually seen some of his video footage where he was recording surfers, but had no idea it was him, and or that it was his footage. So when I was on his website, I thought that was really cool. But so what exactly, like, for example, he's doing in this picture is he's tinkering with the manual input of this gyroscope, trying to make sure that he can get the stability correct, so that when the drone's flying around, and if you have any sort of wind perturbation or anything, that the camera doesn't look shaky when you're watching the footage later. So that's just one example. This would be avionics that he's working on. Other examples of control systems, it's really endless. Pretty much anything you can think of that has a moving part is going to require more than likely not require a control system to go with it. Some of the kind of basic ones that popped up off Google would be avionics, powertrain systems, robotics, automation in the production line, and embedded systems. Those are kind of just really broad aspects of what you can do with control systems engineering. And yeah, like I said, it can get very more specific, and there's almost endless opportunities for you as a control systems engineer in the field. Are you guys seeing my mouse? Yeah. So I put this, how does this arrow work? There we go. I put this diagram right here. It's kind of a basic breakdown, really elementary kind of representation of a control system. So you start with the idea of a reference input, which would be your ideal end state, end result. And then you go through a control algorithm to get that system there. And then the actuator, which actually controls the system. And then you have the plant, which would be the system. And then you add all those together and multiply those together, and you get this output. And you don't know what this output exactly could be. It could be your desired end state, or it could not be. So back in the 1950s, during the Cold War, some engineers came up with the idea of feedback signals, and this incorporates sensors. And right here, it's kind of resembles by one sensor, but this would usually be tens, hundreds, or maybe even thousands of sensors in this feedback signal. And this kind of tells you where your system is working. So how is the end state related to what the actual state of the system is like, and you incorporate that in, and this whole system works really fast, and you try to change, because this is a dynamic system, so it's always changing, and you're always taking signal inputs, feedbacks, and then trying to reach your end state. So that's just really a simple breakdown of kind of the theory of control systems. That's kind of it that I have. If you guys have any questions.
I got a question.
Yeah, go ahead.
I don't know if your perspective on it, but I think we've all, or not all of us, but it's pretty common for us while we're doing projects, like build things with Arduinos or other microcontrollers, which would be resembling a sort of control system, obviously putting like a computer in there almost. But do you know when it becomes applicable to like actually write out these diagrams and get the actual feedback system and stuff like that? Like, when does that become a true resource rather than just like work to do?
Right. So you're talking about the actual picture of the control system diagram. It's more of just a concept to help you understand where you're at in your process, and it's just a big picture idea. So if you ever get lost on thinking where am I in relation to my end result, go back to the diagram and think, am I in the control phase? Is this signal coming from my actuator, or is this signal coming from a plant? How can I add more controls to this signal, to this system, to reach the desired end result? As far as I know, you don't really, these blocks just resemble like very complex, most of the time nonlinear equations that you can't really picture on paper and understand how it works realistically. You use a lot of simulation for that.
Sounds good. Thank you.
I have a question too.
Yep.
Like with this aspect of EE, like control systems, personally for you, like where do you want to apply this like in the future? Like, do you want to mess with cars, or like, where do you want to apply this? What are your interests?
Yeah, I can't really, that's kind of a big decision to make. Like that to me is kind of like the question, like, oh, where do you see yourself in 10 years? Like, I have no idea. So I'm just trying to lay the groundwork, and, I'll take any opportunities that I can find to, progress myself down the line. But as far as if it's automation or automotive or aerospace with avionics, or it could even be like embedded systems with like a company like Neuralink or a biotech company. All of that sounds interesting to me, and I don't have enough experience in those fields to say, okay, I want to do this one for sure.
Dude, I'm on like the same boat like as you, like the exact same boat. Like I'm just so interested in everything, and just it's so cool how like engineering can be applied in everything in this world.
Everything.
Yeah.
Yeah.
So.
Sorry, I'm gonna interrupt. Hi, I actually posted in the chat. I graduated in 2018 controls, and I step in every once in a while because I'm still in contact with Haggerty. But essentially controls you can do with everything. I worked avionics at Boeing for a bit. I now work with satellite systems. So it's a little bit of communications as well. So, I mean, when you choose an emphasis, it's really about practicality and because electrical is so abstract, right? Like there's so many different ways to look at it. After you take in 310, you start to understand control systems in block form. That's why the block form seems so simple to look at right now. But when you essentially everything turns into a transform function, and all your components are just Z, right? Impedances. So when you understand in that sense, you can understand design work. You can most electricals that get out into the industry start out as systems engineers, which is kind of like the basic role that you'll get into. I think I'm on my 3rd or 4th year as an engineer, and it's now getting a little more complex. I believe EE 470 is still emulating the satellite system. So when it comes to controls, you're optimizing, you're making it simpler based off time or target values, like he said. And controls is essentially everywhere. It's in automotive. You can work at places like Tesla, GM Motors, what else? General Motors. Who else did I interview with? Honda. It's huge. Automation's huge in Southern California. They have deep learning neural networks. If you get into machine learning and embedded systems, that ties in a lot too. EE 346 ties in. It's one of the hardest classes, I believe, at Cal State Long Beach, because not just because it's Hill, but because you're applying every aspect of EE. Yeah.
Which class did you say that was?
346, microprocessors and microcontrollers. Yeah.
I heard it was really difficult with Hill, but he wasn't teaching it when I took it. and it ended up being like a really easy class for me. And I was pretty skeptical, like if I got the right education in that class or not.
Yeah. Did you take it with Chris?
No, it was a different, it was another guy like Chris. He's also a PhD student and was kind of just going off Mozamdar's lectures, I think.
Mm-hmm. Well, I mean, the concept of that class is like, it depends on, every engineer is different. Some are design spec heavy, architecture heavy. Some are more microelectronics heavy. You start to learn, you don't really start to learn your strengths until after your 300s, which is why it took me a while to decide on controls or DSP. 310 is a really good intro if you guys haven't taken 310.
Yeah, I'm going to interrupt. So I would love to talk about this more. And like we already discussed in the workshop, but let's try to stay on track. We're already a little.
Yeah, go for it.
Sorry.
So let's keep it going, Justin.
Yeah. So I'm done if we want to go to the next speaker.
All right. Thank you, Dakota.
Yeah.
All right. So next up, we got DSP being presented by Christina. So I'm going to give it over to Christina.
Hello, I'm Christina. Sorry, I didn't add too many other things because I didn't have that prepared, but I have great experiences to talk off of, you know? So I currently work at Northrop Grumman. I'm a full-time employee. This is my first month done with being full-time, and guys, it's been crazy. I work full-time a lot, so I work like 80 hours plus 20, so it's like 100 hours 2 weeks. But anyways, back to what I was saying. DSP was actually super great for the application of what I'm doing currently at work. I've been doing a lot of signal processing, which is implied in my emphasis. So we use this program called ADS, which is it's a program that's used to analyze signals that are going through units. And so currently I'm an RDE for a unit that's called a mezzanine board. RDE means responsible design engineer. So that implies that I do all the analysis for power, for signals, for game budget, for a bunch of stuff. And so all of this stuff is like required to be able to get anything up into space. And so in this case, I'm on this program called PTS, which is, we're creating a module that is required. It's kind of like a program that is making a unit that can be used in a bunch of different applications. So usually like if you're designing a unit, it's specific to the program that you're doing. But in this case, it's going to be used for a bunch of programs. So it has to have module design and like all this other stuff so it can be used and like cost effective. And so for my board, it's called a mezzanine board. And get it? I don't know what that is. But anyway, so I don't know what that means.
I'm so sorry. I thought that was I was saying like let's get it because Kevin said let's get it.
Oh, okay.
Yeah.
I get it.
I thought I was talking to just Kevin.
The board that I'm doing is a mezzanine board. And so what this does is it has a bunch of buffers on it. And so all of the signals that are going through the unit has to go through my board to go to other units. So it's not necessarily a board that relies greatly on power that's being distributed to it, but it mainly is most important because it has to have signal integrity. And so the way that we analyze signal integrity involves like a very module testing simulation design, which requires you to like put, okay, I'm using this receiver, this buffer, and I'm going to put this connector and this connector, and then I have S parameter files. And so S parameter files are used based off of like testing, which is, so if you have a STP file, that means that you have a single port. It has 2 ports on it. So you have a matrix of different types of data. And so you use that to analyze how well it's going to let your signal survive throughout the simulation, which then is used on the actual unit itself. And so it's really exciting because you get to see both the test version of it, which is like based off of what you get off of the key site or whatever it is that you're doing to test the unit. And then you also have it based off of like what the vendor provides. So like for my board, we have a receiver and a driver. And so those are both files that are provided by the vendor itself. And so that kind of is like how the vendor tests whatever it is that the driver and receiver components that they have. And then they use that to decide like, okay, so if this is how they saw this part to work, will it also work as well as we want it based off of our parts as well? So it depends on like how the line like lays out and everything to decide, okay, so this is going to be good enough for space or not good enough for space. And if it isn't good enough and like adjustments can be made to the receiver and the buffer to accommodate to make the signal better, or you can just redesign, which is like not what you want to do, but in some cases that is the path that you have to take to make the signal okay. And so that's like super applicable to my emphasis. And I think that it was really good to have the classes that were required to do that, to understand like, okay, this is what an S parameter is. This is what a signal I needs to look like, and all these things to understand the math for it. Because like doing these simulations is cool and all, like to see the I and everything, the data I, which is like this, like it literally looks like an eye. It's crazy. And so you can also apply like IEEE mask to it to show like, okay, so this is within spec for if it's going to be okay. And then when it fails, like this, the program itself will say like, okay, this is good, or okay, this is bad. And then you have to still accommodate to make it be okay for specifications and stuff like that. And so like what's cool is that all the classes that you take at Cal State Long Beach, those actually explain the math that's required to do the simulation. So and then like I think it's really important to understand what it is that's being outputted. And like I think now as I'm doing analysis and I'm like a responsible engineer and everything, like it's more important for me to go back to all my notes and stuff to be like, okay, this is what this meant, or like, okay, this math that we learned at this one point isn't like, I didn't pay attention as much and now I regret it. So I think that it's really exciting to be able to see the math that's applied with like signal processing, and then also see like the test setup for it, because it's really cool. And like the like labs that are required to do signal processing are like really interesting, because in some cases you have to like have specific type of temperature to like withstand like space environment, and also like there's like crazy other stuff where you like have to burn in modules to like when things come in being produced and stuff like that, you have to actually burn the module to make sure that it will handle space conditions, but also like it kind of bakes out all of the things that are like may come in when you get the module itself. And so there's just like a bunch of crazy different like things that can affect how well your module or unit will work. And like it's interesting too, the process that's required, because it's like, okay, if you're one layer of the unit, like you have to work with 5 different engineers on 5 different boards, and then like you have like a backplane board, and so like all of that has to work together to make sure that like the module itself works. So it's like, okay, if you're doing your job and you're doing it well, it doesn't matter if someone else is doing their job and they messed up, because then it's all on everybody else for it to work, kind of thing. So I think that was really good experience to get like DSP knowledge and stuff like that, because then I have a better understanding of how things work. So then I'm not the engineer that's failing. So yeah, that's all I have to say.
Do we have any questions for Christina?
So what company are you working at right now?
Oh, you know, I'm working at Northrop Grumman.
Okay. Oh, it does say right there.
Yeah.
So what you would say, would it be okay to say that you're using both like DSP and controls theory hand in hand for that RDE system you're working on right now?
Yeah, I think so, because when you get assigned a board, like usually there's a bunch of other aspects of the board that you have to know how to do. So like my unit is mainly digital, but there are aspects of it that are digital signal processing stuff, or I mean like just like more like higher speed signal processing stuff. So like I think that both aspects are really important to understand the overall like workings of a board, because there's a lot going on a board. It's and it's just like you're in charge of it, so you have to learn.
So how much do like the other concentrations play into that, like the embedded applications or embedded systems, and then like the electronics?
They all have a big part, because especially with the signal processing that I'm doing currently, it's actually an FPGA that's outputting the signal itself. So I have to program the FPGA to make sure that the signal that's coming out is correct. And that requires understanding parameters that are provided by Keysight to program into. So they all go really hand in hand.
What language do you use to program the FPGA?
So right now it's just like the processing that I'm doing, they give you a model, and then so with that model you get a user guide, and with that user guide they tell you how to set it up, like with certain kind of like there's blocks that are involved, and each one has a different file from Keysight. And so the programming part of it is just adjusting the like limits or like like 0 or 1s of the driver itself. So it's in it's an S parameter file program kind of thing. So it's like you just use Notepad to edit it. But if you're better at ADS, which is the program's name, you can actually program ADS, and it'll program the FPGA and other parts of it to be like what you want. So I'm still learning that aspect of it, but I do remember learning VHDL in school. And so and that's actually really, really important too, because all the boards use FPGAs. And so if you have that knowledge, you should definitely flaunt it. Like, hey, I know VHDL, I know all these things, because not everybody does, especially not the old heads. So yeah.
And how's the first month of full time then?
Oh my God. My coffee intake has gone up so much. I was doing like 1 cup a day because I was really trying, and now I'm at 5 somehow. Like I bought a coffee maker and it just like, but
no,
so
she's cracked out, man. She's cracked out right now.
You gotta start cold brewing.
Oh my God, it's so much worse. But because what I do is I work from 8 to 6 straight, and I eat a sandwich, and that's it. I work the whole time. And then I get a break at 6 p.m. and I take an hour break to eat dinner, and then I go back. I keep working. So I do a 12-hour day.
Back on site?
Wait, are you on site? Yeah.
Yeah, I'm on site the entire time.
You need help, my man.
Dude.
Is that in Redondo?
Yeah, I'm in Redondo Space
Oh, okay,
Park.
that's the drive.
Hey, Christina, I got a question.
Are you
What's it called? Are you doing the vibration testing and all that stuff, or is that an external company or someone else?
So we do vibration testing, but it's not at Space Park, or it might be at Space Park. I think they do it at Space Park, because the unit itself, we're so far from programs. Oh my God, it's so so we were you have a schedule, right? And you need to get things done. And so we keep changing our board so it stops the actual getting it produced part of it, because program keeps changing what they want or adding things. So we haven't even gotten to the part of okay, this is how we're gonna test it, or for environmental stuff yet. We're still at the okay, we're accepting these resistors, these capacitors, this is the signal, we did the power integrity analysis and all this stuff. So we haven't even got there. But from previous experience, I think that the smaller level vibration testing we do at Space Park, but for sure full satellite vibration testing, we do that in Florida, because when Jay West required vibration testing, it actually failed. And so it had to get shipped all the way back to Space Park because we had to fix it, because what had happened was that the epoxy failed, and so all of the screws that were attached to the overall satellite unit fell into the unit itself. So we had to clean it out and everything, and then reapply all the epoxy and stuff and re-qualify everything. So yeah.
Thank you.
Well, I have one question. So do you work 12 hours because they want you to work 12 hours, or you just overstay past 8?
So when I applied, or when I became full-time, I was given the decision to work my program currently or another program. And so what I did is I chose to work full-time for this one program, and the other program that I didn't work for, they're like, hey, what gives, you left, kind of thing. And so they're like, okay, well, if you want, we can let you work EWW, which is extended work week, to also work our program. And so I didn't want to burn any bridges or anything, and that program has been really good to me. So I was like, okay, I'll work extra hours for you guys. So I work a full program on like the full day, and then like after hours I work my night shift job is working this other program.
You're crazy.
I understand all the caffeine.
You need to relax, Christina.
Yeah, you should go like
How
bust a
long-
kickflip or something. Go
We-
practice your kickflips.
We gotta keep it moving.
I know I've been like falling so behind on skateboarding. It's so sad. But it's good. Okay, so like people when they first start working, like the big thing is that you want to work as hard as possible initially so then you make those connections versus later on. So like that's the plan for me, is to just like work a ton in the very beginning of my career so I can make, you know, those like career gains, and then like after chill, you know, like
And then go thrash.
yeah.
I got you.
Well, we're gonna talk more about it after. Let's keep it moving. We don't want to run out of time.
All right, thank you, Christina. Next up, we got Andrew presenting power. So I'm gonna hand it over to Andrew.
Okay, give me a second. I'm gonna move my screen over here because I'm looking, my monitor's over here, but then I have like a second one, so give me a second. Okay, that's a little bit better. Yeah, hi everyone, my name is Andrew. I am currently a third year. I should be graduating, third year electrical engineer, right? I should be graduating in spring of 2022. And I chose power because I started working at Edison. I wasn't sure which emphasis I wanted to go into because I hadn't taken the courses where you explore each of the different classes yet. But then when I started working at Edison, I'm like, okay, I might as well go into power because, you know, that's where the job's at. And I end up, and I really like what I do, like at my job. So I'm like, okay, this is a good place to go into. So in terms of like my job, so I started as an intern at Edison back in summer last year, and like, you know, COVID was happening, right? So everybody was home, and for the first couple of weeks, I was basically like on the computer just entering data onto Excel, like for 8 hours a day, right? And you can imagine, like, it's not like the funnest work ever. And I'm thinking, oh, is this like what being an engineer like at a power company is like? Then I got approved like after about like I think it was 3 weeks actually. I got approved to go inside the lab, and I've been working on like multiple different projects. And the company I work for, they're called Transmission and Distribution Innovation, and we implement like new technologies in order to improve the grid. Like one of the projects that I'm working on, and it's like in the back of the picture on the slide. It's called an RIS, so a remote integrated switch, and this system is it's built in order to mitigate power outages due to like faults occurring from either a power line falling or from like equipment failure. And basically, this system, what it does is, so coming from a substation, you have like a circuit where power is being distributed from. So you have like a substation, then power is being distributed to, like, let's say different residences or businesses. The system is designed to isolate different or like a fault activity by opening up the circuit around the fault and then restoring it through a different branch. And I've been working on the system where we've been training. Well, in this case, the thing is called a double, like in the back, like right behind me on the left side of the photo, where the cables are coming out. This thing is called a double, and we're training it to using machine learning in order for it to simulating different fault conditions. So ever since I started working at Edison, we simulated about 300,000 simulations where like a fault would occur like in a circuit, and the system would have to like remap itself using peer-to-peer communication in order to restore power. And the way it's at right now, if a line goes down, let's say, like in the simulation, it can restore power in about 40 seconds. But our goal is to eventually get it down to restore power within a single cycle. So you wouldn't even notice any difference if a power line were to go down, unless you're in that area, of course. It's been mostly hands-on, which I really love working hands-on with projects. And it's in terms of like work, it's funny, like, because I go to work at, let's say, like 8 a.m. and then it's like before I know it's already lunchtime. I'm like, oh shoot, like it's been 4 hours. Like what the heck? Like where did the time go? It's like I didn't think that it would be so fun to I didn't think that work would be as fun as I thought it would be. So it's definitely an experience, and there are multiple projects I'm working on besides this one, but this is like the big one that I've been getting into. So yeah, I mean, that's kind of what I've been doing recently. So what else should I?
Any questions for Andrew?
Yeah, I got one. So I, to my understanding, you said you're taking 350 now. Is there like a technical part that you're learning about in that 350 class, or something that interests you that also is related to your job?
Yeah, we have to deal with power factor correction, and there's an issue where so certain certain people, or I guess customers, you can say, like in the SCE territory, they have something called code gen, which is customer generation, where basically they send like, if you have solar panels, let's say, you're sending power back onto the grid, right? The problem is, like, Edison has to deal with that load in order to, like, they have to do like reverse like power factor corrections. It changes like the phase angle like on the line, and it's not a problem for small residences, but you have these giant like solar farms, let's say like in Lancaster, or there's even like a big one in Irvine. So 350, like it since I've been taking it's only been a couple of weeks, but we definitely use like the principles like on site. But in terms of like actually using like stuff I learned in the program, like in the EE program so far, I would say the only thing besides the practical aspect, like working with your hands and like just connecting things and like running a program, the biggest thing that I've used is the Laplace transforms and like differential equations, which I didn't think it was going to happen, but we do have to do the math for some of the projects, like on a whiteboard. But yeah, 350, I say it's pretty what is power, right? So, and no credit utility, so it's pretty well connected.
Perfect. Thank you. That was a good answer.
Any more questions? All right, we're moving on to our last person, Michael Goodhart, and he will be representing electronics. So Michael,
That will be me. I'm down right in the bottom right of this presentation. You can see me and my two beautiful brothers. I will be representing electronics. So this hasn't been said. I think we probably should have said at the beginning of it. But for those that are not aware of how the emphasis works, basically, as you're going through your EE program, you go through a 300 series. So this includes like 330, 350, 370, 386, 382, where you kind of get an understanding of the different emphasis. 330 representing electronics, 370 controls, 386 DSP, 382 communications. And so you kind of get a whole spectrum. I don't know if I missed one in one of those explainings. But basically then you go, the emphasis is trying to prepare you for some of the work that you might actually do in your job. And so whether you might go into specific, you might become a controls engineer or a power engineer, or work for a company like Edison, like Andrew, or something like that. And so that is kind of the goal that they had, was setting up this emphasis thing. And then the emphasis thing is you have one capstone class, two classes that are in relation to your emphasis, and then one extra elective class that can pretty much be from anything. And so even though you emphasize in electronics or you emphasize in controls, if you're still interested in doing, let's say I emphasize in electronics, but I'm still interested in a lot of the controls classes. One, I still get one extra class. I can basically I can do an extra class that's in any other emphasis. But also a lot of the you can also double emphasize, but you can also, a lot of them overlap. So I know there are people that are doing, I think power and controls was a pretty common one. But now let me speak on electronics. So basically, in my interpretation of electronics was always that this is what I was thinking of when I thought of an electrical engineer. These are the people who are designing those analog and digital systems, going into the nitty-gritty of the actual circuits, running simulations on it, getting an understanding of how it will work, and really getting into it. It's the people that are designing those chips in the top right, those CMOS chips that you use for 201 or that you use to put together those gates. Someone has to design those. And so a circuit engineer, an IC design engineer has to go in and make that. And those are kind of the jobs that you would look for an electronics, and specifically for the emphasis of electronics that we have at Cal State Long Beach. When I was looking at the different courses that they described specifically to get a better idea, you were learning about the theory and the actual application of the designing of these ICs, of these analog and digital systems, of the capacitances, the problems that you might come into, the systems you might use. So in the curriculum, it's learning how to use PCIce. It's using how to use computer-aided circuit systems or design and analysis. It's learning both the theory and the application of it so that when you actually get to the industry, you are ready. And so, for example, the top left picture is a PSpice. So you're building the circuit and now you have to run implementation. You have to run analysis on it, kind of get an idea of how it actually works so that when it is made, because obviously you're making them as small as possible as you are trying to sell these things, and obviously size, you don't want something that's big and clunky. You want to make it so that it's able to, it's working fully, and that way it can be sent to an actual fabrication place, and then they can make it for you. As for the bottom picture to the left of my beautiful brothers, that is the VLSI. It's electronic design tool, basically actually putting it all together. You will learn how to both PCB, but also actually making it into actual chips. Those are kind of part of the degree and the emphasis that you will be learning and kind of learning about it. I know there's a subclass where they learn more about mechatronics, which is the design and the ICs and actual electronics that go into robots. Like an example would be like making like one of those robot dogs or something like that, like the mechatronics. And so that is a specific class, but that is not part of the capstone. And so that would be one of the choices that you could make if that's a field that you would want to go into. But like I said, this is kind of what I was imagining when I viewed being an electrical engineer. It's more like very technical. It really is getting into the circuit. If you think of 330, it is you can think of, you really dive into BJTs and transistors, and you're looking at the even more in depth, the parasitic capacitance that slow down that process. How do you speed it up? What is actual voltages that go through it? How do you design the voltages to work with one another? Stuff like that. And so that is really what entangles this electronics emphasis. And then I put a couple job descriptions in the bottom left. You can look at those. A lot of them are designs. I know Intel is a big company that you would look at if you're an electronic emphasis and you want to go into this field. Intel would be a good one. They require a lot of electronics emphasis in that kind of a sense. Does anyone have any questions for me?
I got a question.
Yes, no.
What's been your favorite electronics class so far?
I would say, you know, I would say I enjoyed 435 because it all put it together for me. That was a microelectronics class. I really felt like that's where I was like, oh, that's what's in these chips. That's what's how we made these things in 201. Like this is how it all worked and stuff like that. But I mean, for all the classes that like, especially when you go online, I think like the spices have become more applicable. And I really have enjoyed learning how to use spices and actually understand the spice softwares, the simulation softwares. I think those are just helpful for all of it. Like I use that for 400D, I use that, it's just helpful before you get the parts to run it through a simulation.
For sure.
Yes, Christina.
How did you get so good at PSpice? Like what? Because I know, or like it's really useful at work and stuff like that, but like I don't know what the best sources of knowledge or where to get it. So where would you recommend to get it?
Yeah, I think my advice to everyone when they go into engineering is it really is the group that you surround yourself with, because if you surround yourself with good people, then they're going to help you. And I know when I learned spices at the very beginning, I was horrible. I was very, very poor. And I remember one of my friends, Danil, stayed up much later than I and wanted to learn it a lot better. So he definitely helps me in motivation. And so that helped me a lot. But also there's a lot of examples, and I think just plug and play, really. It's not the most friendly, and especially a lot of professors aren't the best with it. But I mean, you find a couple that are, and you just kind of ask them for advice and try to get where you can.
I think that's great advice. Thank you. But for someone that's not in college.
Oh, for not in college.
Yeah.
You know, I would have to look through a lot of tutorials. I personally have not, but I'm sure there are some out there, especially YouTube ones. And then I would advise starting from the very beginning. So like doing a simple circuit. We have our workshops on, oh, there you go. We have our workshops on the IEEE Discord. So like learning at the very beginning, using IEEE would be a great resource to ask us for help. Obviously, I'm still there. We have Ifoma, who ran her own workshop on using LT Spice, where you learned how to simulate the actual circuit. But starting at the beginning, I think the workshop that we held for IEEE is a great like beginning step, kind of using that step by step, and then trying to grow from there, trying to make more complex circuits, and then you continue to grow.
Thank you so much, Michael.
You're welcome. Any other questions?
Yeah, how do I get blue eyes like you?
No, I don't think I can make comments while it's recording, but I think you look just good enough. All right, Kevin.
Thank you. Contacts.
Yeah, you get contact.
Smart.
All right, Justin, you want to close this out then?
All right. Well, since that's the end of it, do we have any last minute questions? If not, I will conclude this meeting. All right. Thank